Okay, for this lecture, we're going to be talking about the early developments uh, in quantum theory. But before I get started on that, I'd like to talk a little bit about what quantum mechanics or quantum theory is and compare it to classical physics. So the most basic definition of quantum theory or quantum mechanics is that it describes the physics of matter at very small length scales. So let's compare and contrast some key features of quantum mechanics versus classical mechanics. In classical mechanics, as we previously discussed, we can treat systems as being consisting of point-like particles, almost like a geometric point or a collection of such points. Whereas, as we'll see, in quantum mechanics, particles are represented as these sort of fuzzy, spread out wave functions. In classical mechanics, we can know, at least in principle, exactly what the position and momentum is of each individual particle in the system. However, as we'll see, in quantum mechanics, there's a sort of built-in uncertainty in position and momentum, that there are some limits on what we can know about the position and momentum of a particle that are not due to sort of some shortcomings in our experimental apparatus, but rather are sort of a fundamental feature of the way matter behaves because of these fuzzy spread out wave functions. So in classical or Newtonian physics, we have this picture of this kind of predictable clockwork universe where once we know the position and momentum of a particle at some given time, we can map out exactly what the trajectory of that particle is going to be in principle for an infinite amount of time. And in practice, for very large amounts of times, for instance, in planetary orbits, lunar orbit, so on, we can map out the behavior on large scale of large collections of mass to very good precision for a very long time. Then the next aspect of, but then the corresponding aspect of quantum mechanics is that we have limited predictability, again, related to this uncertainty in position and momentum. And we have a universe that is governed by probability, where a particle can sort of seemingly be in one place and another place at the same time. There are these so-called quantum leaps, and this, if we accept the quantum picture, is the way the universe works. In classical mechanics or Newtonian mechanics, of course, the governing equations are things like Newton's equations or Lagrange's equations. Whereas in quantum mechanics, the equations of motion are Schrodinger's equations. There are a couple of them. We'll primarily be talking about the time-independent Schrodinger equation, but there's also a time-dependent Schrodinger equation that tells you how a particle behaves over time. In classical physics, in Newtonian physics, energy is continuous. You can think of kinetic energy. See, look at this plot here. We can have kinetic energy as a function of velocity, and kinetic energy is 1/2 mv squared, and there's no restrictions on what velocity the particle can have. It's It's continuously variable. You can have any number, any value. And so you get this sort of parabolic relationship between velocity and kinetic energy, and it's a continuous functional relationship. Whereas in the case of quantum mechanics, we find that energy is quantized. There are discrete energy levels, such as, for example, in the case of the hydrogen atom, you have, say, a 1s energy level here, and there's a 2s level there, and there are 2p levels here. And so there's sort of a ladder or a series of possible allowed energy levels, and the energy levels between those are not allowed for a given system at a given point in time. So that's just a few basic observations about these theories. We haven't really gone into why quantum mechanics is this way yet. And to develop that, we're going to start talking about some of the storm clouds on the horizon, some of the problems with the classical theory that started to appear. And by the late 1900s, there was a somewhat disturbing number of observations that did not appear to be compatible with conventional physics as it was known at the time. And this is despite the fact that Newtonian mechanics, thermodynamics, and electrostatics, electromagnetism theory, Maxwell's theory, was very successful and helped to usher in a wide range of advances. And these were theories that were somewhat simple. They derived from very small equations, and they could explain a lot. So these were, very impressive theories. Nevertheless, they didn't seem to account for some of the things that people started to observe, such as electrical conductivity. Right? Some kinds of materials are conductors, some kinds of materials are insulators, and classical physics, sort of physics up until the quantum theory, could not really explain why metals conduct electricity and insulators don't. And similarly, things like ferromagnetism, where does that come from? Why are some metals ferromagnetic? Why are some materials paramagnetic? Other materials are diamagnetic. These observations couldn't really be explained other than some vague notions of there being little magnets inside matter. Another issue is the sort of basic optical properties of matter. The fact that you might be wearing an orange shirt. Why does that shirt reflect the light associated with orange color and absorb other wavelengths of light? This couldn't be explained using what was known at the time. Gases have heat capacity. Often a monatomic gas will have a constant volume heat capacity of 3/2 R, where R is the ideal gas law constant, 8.314 joules per mole per Kelvin. For diatomic gases, the constant volume heat capacity is typically 5/2 R. This did not have any rational explanation. And it hinted at something's going on here. and yet physics couldn't provide any answers. Similarly, elemental solids have a heat capacity of CV equals 3R. Most of them are very close to that. There are some deviations, but the fact that so many materials had a heat capacity of about 3R hinted that there was something else going on here, and yet no explanation was forthcoming. The line spectra of various gases in a discharge tube, or similarly observed in the spectra of our sun when viewed through a diffraction grating, these line spectra had no explanation, and they hinted at there being some perhaps important physical explanation. And of course, as we moved towards things like chemistry, there were a number of mysteries. One of these mysteries was the sort of periodic structure of the periodic table. The fact that the notion of atomic number was gaining ground due to work with X-rays. You could assign atomic numbers to the various elements. And of course, Mendeleev, around this time, perhaps preceding when the experiments took place that assigned atomic numbers, was able to construct a periodic table of the elements, showing that certain kinds of behaviors or properties tended to repeat as you moved along this periodic table, and that, you know, sodium has some properties in common with lithium, and potassium has some similar properties as sodium, and so on. And then there are the, say, inert gases. And there seemed to be some regular rule that said, that related sort of atomic number to where a given element fit in this periodic table. And when it fit into it, all of the elements in a particular column seem to have somewhat similar properties. There was no explanation for this. Covalent bonding. So by this time, chemistry had really made a lot of progress, and using some astonishing experiments by just looking at things like boiling points and melting points and so on, and reacting different things like iodine with extracts of oil tar, these early organic chemists were able to come up with proposed structures for things like benzene. They were able to get some hint that methane had a tetrahedral structure, and that it had 1 carbon and 4 hydrogen atoms. And by reacting methane with iodine, they were able to, and then looking at the boiling points of the various, or melting points of the various derivatives of methane, they were able to develop this theory of covalent bonding, showing that, and there was substantial evidence that there were these regular arrangements of atoms to form molecules, and that there was some kind of structure. And there were some sort of empirical theories where you could make some predictions of what was going to happen, various rules about shells and octets and so on, but there was no solid rationale for these rules. And in fact, they were not taken very seriously by a lot of physicists who had a lot of skepticism about chemists' notions of molecules and covalent bonding. Nevertheless, there was a lot of really solid evidence, and there was no physical theory to really explain what was going on. Just some sort of ad hoc rules of thumb. And finally, towards the end of the 1800s, there were a couple of phenomena in particular that are closely linked with the initial development of the quantum theory, and those are the photoelectric effect. J.J. Thomson did the experimental work on that. He'd been preceded by Hertz, and before that by Becquerel with his photovoltaic effect. But Thomson's work really provided a lot of important detail about how matter interacts with light and the fact that electrons can be emitted from a metal surface when it's exposed to light. And there was no explanation for this. Another issue was thermal radiation, the so-called black body radiation. It's called black body because this is an apparent color that objects have when they're heated up. That's sort of independent of what their color is when they're cool. And in fact, you could have something like a hot coal whose color is black, and if you heat it up, it's going to have maybe a yellow or an orange or a white or a bluish type color. And so this thermal radiation, this light given off by objects that are raised to a high temperature, as we see every day in flames and so on, the explanation for this was not forthcoming. So our first steps, so those were all some pretty big gaps in the ability of physics at the time to explain the world around us. And so it was pretty clear that we needed a new theorem. But like a lot of important theories, it starts off pretty small. And the first steps towards the quantum theory are in Planck's theory of thermal radiation, or Planck's black body theory. So we know that if we heat up objects to various temperatures, there's often they glow at some characteristic color. And for things at sort of a little bit above room temperature, they'll be giving off infrared radiation in the sort of micron range. As you heat up a little bit more than that, to several hundred Kelvin, 1,000 Kelvin, you start to get more and more heat produced, and the wavelength of the infrared shifts a little bit shorter to the sort of 0.8 to 2 micron range. And as you heat higher and higher, you get progressively changes in colors. Of course, you get more than one color occurring, but still there's an overall cast to the light that comes off. In the sort of near IR, there may be a little bit of dull red, around 800 nanometer light, 750 nanometer that you can barely detect. As you heat up to 2000 Kelvin, there's more of a red or orange cast. And as you go up to higher and higher temperature, you go through sort of yellow, white, sort of like our sun, and blue-white for objects that are hotter than the sun. And there were a couple of, I'm not going to go into a lot of detail about the competing laws. There's more information in the textbook and online on that. So I'll just jump to Planck's equation. Planck tried to explain this spectrum, this fact that the sort of center wavelength or the peak wavelength of light emitted by a hot object depends on the temperature. And he was toying around with sort of tinkering really with a few different equations. He was tinkering with the Rayleigh-Jeans equation, and the Wien displacement law, and he was toying around with some concepts from a physicist, Ludwig Boltzmann, and who had developed something called statistical mechanics that was kind of an explanation for thermodynamics in terms of the behavior of atoms or molecules. And Boltzmann had these expressions that involved some constant times temperature, some exponential with a constant times temperature, something like this. It would have things like this in the denominator, so I put one of those in there, and he ended up with an expression that could explain, or that could reproduce, not explain, that could reproduce this behavior of objects that are heated to some high temperature. And if you look at this equation, let's see if it's kind of a beast. We've got 8 pi h, where h is just some constant, which we now refer to as Planck's constant. It wasn't called that at the time, it was just a constant. 8 pi h times nu over c, where nu is the frequency of the light. So by this time we knew that light has a wavelength, it has a frequency, it travels at the speed of light. All of that was known. And so in the numerator you have frequency to the third power, and in the denominator you have this temperature dependent term where you have e to the h nu, again that frequency, divided by some constant, Boltzmann's constant, which is the ideal gas law constant divided by Avogadro's number, shown here. And that was in the denominator. And so if we sort of take apart this equation at low frequency, this intensity, the spectral density or intensity rho, is proportional to the frequency cubed. And then at high frequency, this term in the denominator starts to dominate, and you get this sort of exponential decrease in the spectral density as the frequency increases. Okay, so putting those two pieces together, you can see we get this rho as a function of the frequency nu, and at low frequencies it's increasing roughly cubically, then it sort of flattens out, and then there's this exponential tail where it sort of tails off at high frequency. And this seemed to match very well with the experimental spectra of various hot bodies, including the sun, flames, various temperatures, hot poker stuck in a flame, things like that. And it was very successful. One of the implications of this was, Planck was just kind of working on this obscure problem that was sort of related to thermodynamics, but there was this interesting implication that perhaps this hot object has little oscillators in it that have fixed energy levels. So these would be like little particles on a spring or something like that, that would be oscillating at some fixed frequency, and that the energy associated with each oscillator would be given by some integer number times some constant h times the frequency. And that just seemed like a curious result. The implications of that were not clear. However, it was a concept that was out there, and that Einstein sort of took it and ran with it. And it is sort of the first clear evidence in sort of by looking at the math and looking at the spectrum that maybe there are discrete energy levels in atomic or molecular systems. So let's move on to the Einstein's theory of the photoelectric effect. So this was in 1905. And it's based on an experiment by J.J. Thomson, where he had light coming in, impinging on some metal cathode or metal electrode in a vacuum tube. And there were two electrodes. They were connected together in a circuit, together with a voltage source and a current meter. And it was found that if you turned on the light and you selected a particular wavelength of light or frequency, that electrons would sort of travel through this tube and be incident on the opposite electrode, and then you could measure a current. And that the current was proportional to intensity. But the interesting thing is the voltage. You could shut off this photocurrent by applying a sufficient retarding voltage that would sort of slow down these electrons, that would give them an electrical push, an electrical potential, electrostatic potential that would stop the electrons and keep them from arriving at the opposite electrode. And that this stopping potential was a measure of the kinetic energy of the electrons. And there was no explanation for this prior to Einstein's theory. And Einstein came up with a very simple expression saying that the kinetic energy of these photoelectrons is equal to h, so he borrowed Planck's constant, times the light frequency minus this work function of the metal, which Thomson showed that you had different kinetic energy of electrons for different metals. And so this work function, it's a characteristic of the metal. In some ways sort of not particularly important. The things like sodium have a lower work function, sodium, potassium. Other metals, copper has a higher work function, so on, silver. But so anyways, Einstein's expression was the kinetic energy, or this sort of stopping energy supplied by this voltage, was equal to h nu minus the work function. And so implicit in this function, in this relationship, is that light exists as particles or bundles of energy. It's not just sort of a continuous wave of energy. There's actually little bundles of energy, and that Einstein referred to these bundles of energy as photons. I believe he coined the term. It might have been somebody else. But in any case, they're called now photons. And that the energy of a photon is h nu, where nu is the frequency, or hc over lambda, which you can derive just based on the fact that light moves at the speed of light, and so on. So there's a relationship between frequency and speed of light and wavelength, and so you can use either of these expressions This is a very important relationship. We will use this relationship over and over again in this course. This is called the Planck-Einstein equation, and so that's why I put a box around it. Or you can just think of it as, what's the energy of a photon? But for some people it helps to give an equation a name, and so we'll call this the Planck-Einstein equation. Makes it easier to Google it, that sort of thing. Okay, so the implications of Einstein's work on the photoelectric effect were that Planck's oscillators were not really part of the object, they were actually associated with the photons emitted by the object. And those were where the h nu was coming from. And the other implication is that light is both a particle and a wave. We already know that light is a wave because it diffracts light. And so this is the first clear evidence we have of a wave-particle or particle-wave duality in nature. With that, I will pause the lecture and move on to the next lecture.